Welcome back to part 2 of our explainer on hazardous area ventilation. In the last session, we really dug into the fundamentals of natural ventilation. But today, we're taking things a step further. We are moving right past the theory and diving into the hard math and the rigorous paper trail required to make these facilities genuinely safe to operate. So, a quick recap. Last time, we established that wind does most of the heavy lifting outdoors. As long as you've got natural ventilation, specifically wind speeds of 0.5 meters per second or greater, it sweeps the hazard away and dilutes it incredibly fast. But in closed spaces, well, they're a completely different beast. You obviously can't rely on a fresh breeze inside a sealed pump room, right? You need mechanical help. And here's the absolute golden rule for that. Simply saying, hey, the fan is running, is never, ever a valid engineering justification. You need real, calculated numbers.
All right, so what are these actual numbers we need? The first crucial building block is a variable called VZ, which is the theoretical minimum dilution volume. In plain English, this is the exact volume of fresh air you have to pump into a space to dilute a specific flammable gas release down to a safe concentration. Specifically, you're trying to push it well below its lower explosive limit, or the LEL. If your mechanical ventilation system can't supply this exact volume of air, you aren't actually mitigating the hazard at all. You're literally just moving dangerous explosive gas around a room.
Then we have our second critical variable, which is T, standing for persistence time. You can think of T as a ticking clock. Because, think about it, if a valve stops leaking, the hazard doesn't just magically vanish that very second. Persistence time tells us exactly how long that explosive gas cloud is going to linger and take to fully disperse after the release has officially stopped. Now, what's really fascinating is how these math concepts translate directly into the physical world, and we see that through the volatility release rate matrix. Just look at how fluid temperature and vapor pressure define the category, and then combined with the mass release rate. If you've got a highly volatile fluid releasing at a really high mass rate, the math dictates a massive hazard radius. We're talking up to 30 meters or about 100 feet. This isn't guesswork. This matrix shows exactly how the physical properties of a leak literally dictate the physical dimensions of your hazardous zone.
Okay, pause right here, because this next point is a major warning that trips up even highly experienced engineers, not just beginners. I'm going to read a quote directly from the API 505 standard, Annex G. It says, "Combustible gas detection shall not be used as the basis for determining the classification of an area." It is a huge myth in this industry that you can just slap a fixed gas detector on a wall and use that to shrink or remove your hazardous zone. The standards strictly forbid it.
To be absolutely 100% clear, gas detection does not equal reclassification. Don't get me wrong, fixed gas detectors are fantastic tools. They alert operators, they sound alarms, they can even automatically isolate equipment. But they are strictly an auxiliary backup protective layer sitting on top of your classification. They never substitute for doing the proper ventilation calculations from the start.
If all this fluid dynamics talk is feeling a little heavy, let's ground it in a relatable, everyday scenario. Think of your bathroom after a really hot shower. V, our dilution volume, is essentially asking, how big does this bathroom exhaust fan need to be to clear out the steam before it fogs up the entire house? And T, our persistence time, is asking, how many minutes does the mirror stay fogged up after I actually turn the water off?
It's a straight-up cause and effect relationship. A weak bathroom fan means a longer fog time on your mirror. In the industrial world, a weak mechanical ventilation system means a longer persistence time. And a longer persistence time directly extends your hazardous window. If the gas lingers longer, your area classification absolutely has to become more severe to reflect that extended danger.
So the math is established. The next challenge is actually proving it. This brings us to the famous paper trail. All these complex calculations we just talked about have to be formally recorded. For any compliant facility, this gets compiled into 3 mandatory deliverables. Step 1 is the hazardous area plan. Step 2 is the source of release schedule. And Step 3 is the X equipment register. Let's break these down.
First up is the hazardous area plan. These are the actual engineering drawings of the facility. You'll notice there are standardized hatching symbols used here. The math we did earlier visually dictates exactly where these go. Zone 0 is mapped in a dense red pattern, Zone 1 is an orange crosshatch, and Zone 2 is yellow. These are basically 3D envelopes that map out the calculated risk directly over the physical structure of the plant.
Our second critical document is the source of release schedule.
You can think of this thing as the master spreadsheet of potential chaos. It tracks absolutely every potential point source leak in the entire facility. For every single valve, flange, and pump, this schedule lists the equipment tag, the fluid properties, whether the release grade is continuous, primary, or secondary, and exactly what that calculated hazard radius is.
Finally, we have the ATEX Equipment Register. This is the ultimate proof of safety. Once you know your zones and you know your gases, this document proves that every single piece of electrical equipment installed in that zone has the right certification to actually survive there. It tracks the IP rating for dust and water ingress, the specific X protection type, the gas group it can handle, and its maximum surface temperature class.
All right, let's pause for a quick thought experiment to see how well we're connecting the math to the paper trail. Imagine you are reviewing a design, and your ventilation calculation shows that the persistence time, our ticking clock, T, is much longer than you initially assumed. What should happen to your hazardous area classification? Take a second to think about it.
Got it? You must extend or upgrade the zone. Because that gas is lingering closer to its explosive limit for a longer period of time, the classification inherently becomes more conservative. So maybe your Zone 2 becomes a Zone 1, or maybe the physical radius gets pushed out by another 3 meters. The golden rule you have to remember is let the calculation drive the drawing, never the other way around.
So, look at how all of this comes together. Before this, you might have just been looking at a bunch of acronyms, but now, you can run the full point source method from end to end. You can find the sources of release, grade them, run the vital ventilation dilution and persistence time math, and actually compile the 3 official documents that prove the facility is safe. That is the entire logic behind every hazardous area drawing you will ever review.
But, theory and paperwork on a nice flat 2D diagram are one thing. Massive offshore steel is a completely different story. Next time on The Explainer, we are going to apply everything we've just learned to a real-world floating production unit, an FPSO. If it takes this much math to classify a static room, what happens to your hazard zones when your entire facility is pitching and rolling with the waves? We'll dive into that next time.